Yeah, good afternoon, everyone. Pedro Pedreira from Meta. Yeah, talking to you again. Let's switch topics and talk a little bit about analytics. So I'm here to present a paper called Shared Foundations, Modernizing Meta's Data Lakehouse. So this paper discussed how we took a data stack that had evolved kind of organically and independently for the last decade or so. And we did a series of projects to make it more efficient and easier to maintain and easier to innovate in the future. This is just kind of describes some of those projects. So I'm going to start talking about some of the recent trends, some of the things that changed in the last 10 years, give some background on how our data stack is organized, describe a little bit about what the Shared Foundations program was, and then talk about some of the consolidation effort. Just some recent trends. I think this is not news from anyone here, but we kind of classify those two things between usage trends or things that are changing from the user's perspectives or how users, the user workloads are changing, and environmental trends, which are things that are changing on the kind of the hardware or the environment in which you run those systems. So of course, there's this data explosion. So 10 years ago, we had petabytes of data. Today, it's super common to see double digits, exabytes of data. Machine learning is becoming the kind of the largest consumer of data management systems quickly, and it's going to surpass analytics in the next few years. There are even more requirements for to access data as fresh as you can and to have really low query latency. There's also this thing called external analytics, which is analytics that you actually provide to end users. So there's a lot more concerns about QPS and even lower latency. Data models are becoming a lot more complex. So now if you look at most of the tables, most of the queries, they all need some sort of complex data types like arrays, maps, structures, and all types of nested data structures. And the query method is also getting more complex. On the other side, on the environmental trends, storage disaggregation is just common table stakes. So this is not even up for discussion at this point. I hope all systems need to provide some sort of horizontal scaling. Elastic compute is also given. Power efficiency is a lot more important. In a lot of cases, the power that takes to run your system is actually cost is higher than actually the capex cost of acquiring those hardware. Global optimization is also more and more important. So instead of just optimizing queries independently or operators inside the query, you need to look at kind of end-to-end user workflows. And another kind of the last thing which is important is engineering efficiency. So as those systems scale, you have more data, you have more variety. You need to find ways to scale the engineering work to support and develop those things. So a lot of the work we're going to present here is how do we make improvements on the engineering required to develop those systems and making them easier to maintain. Essentially, what you don't want to have the engineering efforts to scale linearly with the size of your data stack. So you need to have kind of sublinear ways to make your engineering team more efficient. And the usual solution for this is this open data Lakehouse analytics. I think there's a name coined by Databricks, but that's something that most of the large cloud vendors leverage. Other than disaggregated storage, so you can scale storage and compute independently. File formats are all open, so those things are usually based on very well-defined file formats like Parquet or Orc, but also the metadata APIs are also open. So this allows you to not just scale storage and compute independently, but lets you build different compute engines or different systems that access the same storage, right? So you can have systems to do diverse type of applications from batch to interactive. So you have systems for stream processing and more recently machine learning training that can all access the same data without requiring any data movement or without requiring any data conversion. As a quick background, so if you simplify a whole lot about how the data stack works, and then you do that a couple more times, this is more or less what you get. So all the data starts with the users doing something on one of the websites or one of the applications. There are kind of two main sources of data. One is the transactional databases where you actually store the user data, and the other source is all the actions the users are making, ads they're seeing, and actions they're taking on the website that generate a bunch of logs. There are a bunch of stream processing systems that take those logs, do some kind of processing, and generate logs again. And there are a few systems that ingest this data on the warehouse. So this ingestion system can both ingest logs from this distributed log storage system and create a warehouse or create files on the shared storage. And this ingestion system also scrapes all the transactional databases, creating tables and creating data on the same centralized storage. And on the other side, you have a series of systems that consume this data to do something. So we have systems for batch ETL analytics, essentially munching this data, doing some transformation, generating some other tables and other aggregated tables. We have a bunch of systems that do interactive analytics to generate dashboards and other kind of analytics straight to end users. And of course, more recently, machine learning training is another large consumer of this data, those tables in the same storage system. The problem is a lot of those systems evolve kind of independently and organically in the last decade. And this caused fragmentation all throughout the stack. So if you look at the language layer, because those systems evolved independently, you end up in a place where you had a lot of different SQL dialects. So we counted 6. And this is, of course, very painful for users. If you need to use different systems, you need to learn six different SQL dialects with different limitations, different sorts of tools available. So it's really hard for users to learn about all the kind of differences between SQL dialects. We had way too many systems or way too many distribution and runtimes. So we have a few systems doing the exact same, providing the exact same service for users. On the execution side, which is something we already covered yesterday in the talk, like there was a lot of fragmentation. Each system essentially had its own implementation of the execution, different languages with different restrictions, with different limitations. And the data access was also all over the place. Different systems had data stored in different file formats. Each system had its own library to read and write those files. And in some cases, they were the same, but also not completely compatible. So there was fragmentation all throughout the stack. So how does this impact us? Like I said, it's a lot harder to maintain and to enhance those systems because there's so much fragmentation, and it really hurts our ability to innovate and make improvements to those systems. It also provides inconsistent user APIs for users. So like I just said, if users want to interact with those systems, not just the SQL they use are different, but non-SQL APIs, UDF APIs, they're all over the place. Right? So it's harder for end users as well. So what we did about this is just, well, we created this program called Shared Foundations. So with this set of problems in mind, we created this Shared Foundation program, which you can think as like an umbrella project with a lot of smaller efforts into making the data stack more consolidated and more cohesive. So we had a few principles. First one was fewer systems. So if you have different data systems doing very similar jobs, like we really looked into consolidating them. So trying to identify what are the features we need in all those systems and coming up with something that check all the boxes so we can have fewer systems. Of course, we cannot have a single system. So for all the cases where you actually need to have different systems or different runtimes, then at least share the most components you can between them. And that's the last one, providing consistent APIs. So every API that the user visible needs to be consistent, or at least to the best we can. And the goals are just, well, engineering efficiency. We want to be more efficient about how we maintain and how we enhance those systems, make sure we can innovate faster in the future and provide a better user experience. And I'm just going to go over some of the consolidation effort. There's a lot more details on paper, but this just kind of give an overall idea. So first in the language consolidation, so we had about 6 different SQL dialects, all incompatible between each other with different features, different sets of functions. So it was all over the place. Had things from Presto SQL to HiveQL, PQL, which is something we use for stream processing and so on. So we looked at all those different dialects and we identified that the ideal one would have standard compliance. So closer we could get to some sort of standard SQL, the better. Rich feature set, a lot of those different systems providing SQL dialects, they're incomplete. They didn't support all sorts of features that users need. So of course, whatever we convert to had to support all features that users needed. And something that already had a good adoption to minimize the pain with migration and consolidation. So what we ended up doing was Presto SQL was the thing we had that was closer to those requirements. So we ended up kind of upgrading Presto SQL into this new thing we call Core SQL, which is essentially the same thing, but we added some more extensions to the standard. And when you do that, there are two components that are needed. First one, of course, you need to have a shared parser that can parse and analyze this and create some sort of logical plan or some sort of IR. So we ended up creating a shared C++ library internally that we're integrating in all the different systems. But it also only makes sense if you can actually execute this IR or this query plan, right? So that we're also creating shared execution library, which is I'm not going to cover in details. We already talked about this yesterday. But essentially, we created this unified execution engine, the library called Velox, and we're also working on integrating Velox into all those different systems, from analytics to stream processing, machine learning, database ingestion, data warehouse ingestion. There's a series of use cases. And of course, when we created Velox, one of the main goals was that it should be fully compatible with Core SQL, which is Presto SQL. So in theory, Velox is generic, so you can actually tweak Velox to follow any semantic you want. But we provide Velox and we provide a Core SQL compliant set of extensions and set of functions, which is what we use internally. But you can also, for instance, use Velox to follow the Spark SQL semantic or whatever semantic you want. So look at engines. First, we started looking at interactive analytics engines. So just for interactive analytics, we had 4 or maybe even 5 different engines: Presto, Raptor, Kubrick, Scuba. Kind of following the same methodology, we saw that the ideal system should support full and rich SQL support. Since we consolidate into Core SQL, the system should support Core SQL. It should operate directly on data on the Lakehouse. So basically, we didn't want to have to move this data to some other system, so we can have lower query latency, and it needs to provide low query latency. So we didn't have any systems that provide all those characteristics. So Raptor, Kubrick, and Scuba had a shared nothing architecture. And then the bad part is that you actually had to ingest this data and move data out of the Lakehouse into those systems, which was really painful and had all sorts of problems. So what we ended up doing was we created a project called RaptorX, which is essentially Raptor with local caching, hierarchical caching, and affinity. So that kind of allows us to check all those boxes. And of course, the observation there is that most of the queries are actually repeating and accessing the same data. So you could provide a very similar query latency in most cases. Another thing we did is that users want access to data as fresh as they can. So we made some improvements to both RaptorX and to the Metastore, which are our data metadata API, to allow users to query partitions while they're being ingested. So in the previous system, you had to finalize and close the partition, so the latency was pretty high. So in this system, you have latency in the order of a few minutes, not in the orders of hours or days or whatever the partition says. Of course, because we're developing Velox, the next step was integrating Velox into the system. So we created this project called Prestissimo, which is essentially this Presto with caching architecture running on top of Velox. And this resulted in an engine that is first unified. So we moved all the analytics use cases from Scuba, from Kubrick, from Raptor into this new RaptorX architecture. It gives us language consolidation. So from users, all you need to do is write Core SQL. Provides low latency because of local caches, data freshness because of near real time, and efficient execution because of Velox. So it kind of provide the best of all the worlds and allows us to deprecate a bunch of systems around that. Second one was in batch analytics. So we had this split brain situation where some of the batch workloads still run on Presto and some of them run on Spark for a variety of historical reasons. So the ideal system should provide full and rich SQL support, again, follow Core SQL, but also allow you to provide the scalability needed for batch queries and ETL, which is something that Presto didn't provide because of streaming shuffles and a sort of reasons related to query restartability. So we ended up creating this project Presto on Spark, which is also open source. There's some external information about this, where the idea is you take the Presto front end. So you use the exact same language analyzer, front end, the same optimizer as in Presto. The only difference is when you execute, when you have a query fragments, you actually transform that into RDBs and you run that on top of Spark. So the result of this system is, again, we consolidated the language. So we're deprecating Spark SQL and the old HQL, moving everything to Core SQL. It gives us Spark scalability because we run that on Spark runtime using the shuffles we have for Spark. and the execution, efficient execution because of Velox. On the stream processing side, there was also a lot of diversity because we provided different stream processing frameworks for different languages, for C++, Java, PHP. Some of them are procedural, some of them are declarative. So what we ended up doing was creating this new next generation stream processing engine called XSQL, which again, implemented core SQL because it's something that users were already familiar with and users were asking for. And again, uses Velox for execution. So it gives you this nice cohesive stack. So the result of this was consolidating language, having efficient execution, and having a unified engine, and allows us to deprecate a series of kind of historical and legacy stream processing systems. The last one is around machine learning. So we used to have a custom eval for machine learning that we used to use for pre-proc for training. So essentially when you're pulling the data for training, like all those kind of last mile transformations. So we used to have a specialized engine for that, which we're converging to Velox. But also there are some inefficiencies that became more evident in ORC as we started using that more extensively for machine learning, specifically because in machine learning, you're usually looking at thousands to tens of thousands of features. So the maps get pretty large and you start seeing the inefficiency of metadata. So we created this new file format called alpha, which I'm not going to describe in too many details. Like we're working on a kind of full description of that. But it just makes those types of workflows where you're reading flat maps and you're reading specific features from tables a lot more efficient. So the result, kind of the same thing, we consolidated the language. So on those workloads, we don't use SQL. So we use a non-SQL API, which we're consolidating on the torch arrow, which is a sort of a Python API that more or less look like pandas, but we're consolidating inside Meta. But also nice properties because you're using Velox, all the core SQL functions are available for those use cases as well. So it gives us this really nice consolidated experience to users. Again, it gives you unified and efficient execution because of Velox, and you have efficient data decoding because of this new file format. Did this turn off? Oops. Just working up. This is a conclusion. So shared foundations was a generational leap in the data infrastructure landscape. We made the data stack more modern, composable, and consistent. We deprecated some systems, added richer features and better performance. We kind of removed thousands of lines of code, removed a lot of tech debt. So we really set up our infrastructure to better innovation in the future. There's a lot of things we're still working on. So we like to say that this journey is just 1% finished. So all those projects we described, they're right now in different stages of completion. Some of them are already completed and fully migrated. Some of them are in the process of migration, and some are still under development. So of course, next step is just finalizing and completing all those projects. But there are other things we're looking at. One of the discussions we have ongoing is in the same way as we consolidated or we unified SQL dialects, there are also non-SQL dialects that are starting to pop up and become problems. So things like pandas, PySpark, data frame APIs, torch arrow, and we have a few more internally. So we're also having discussions on how we can provide a unified non-SQL API because of the same reason, because we want to provide a single API for users. We're also looking at UDFs. So UDFs is another API that users use very frequently, and they used to be, again, all over the place, different APIs, support for different languages, completely fragmented. So we're looking into unifying this in a single interface so users can write their UDFs using a unified API and push, and whenever they have their UDFs, so that those UDFs will be available for both batch, interactive, machine learning, and all sorts of use cases where Velox is used. Outside of that, as a last thought, we really think that composability is the future of data management. And we're trying to componentize the whole stack. So we've been discussing about ideas of creating more componentized language layers, things like Zeta SQL, things like the project I just mentioned, execution, we have Velox, but we're also making the data access libraries more componentized. One of the things we've been looking at recently is whether optimizers could also be more optimized. And I know that people are probably going to yell at us, like people are very skeptical about this, but we really think that there might be a way to at least share a common framework that does plan enumeration and some of the cost-based optimizations, and maybe providing ways for users or for developers to extend or to add engine-specific optimization. So there's still a big question, but this is kind of the last part we're looking into, really trying to componentize. And the last thing is also something we mentioned yesterday, as we consolidate all those engines into Velox and having a single execution as a library. If we can have this library able to leverage different types of hardware acceleration, or just using the best or the hardware you have available to the best you can, it's a really powerful architecture because that's becomes available for all the systems. So really kind of hard looking into this. Again, we're just starting. This is kind of things which will be in a few years in the future, but that's kind of the last thing we're looking at. So that's everything I had. I'm happy to answer any questions.
Thank you.